The integral test is another test that we can use to determine whether some series converge or diverge. It doesn't work for every possible series, but it's pretty good for certain kinds of series. It says if a function f is continuous, positive, and decreasing on the interval from 1 to infinity, then if you look at the integral of that function from 1 to infinity, if that integral converges, then the series that's given by sum from n goes from 1 to infinity of f of n, in other words, applying that function to the whole number of values of the series, that series also converges. And if the integral of the function diverges, then the series determined by that function also diverges. So in other words, if you see a series that you're interested in, and you'd like to know whether that series converges or diverges, if the function that describes the terms of that series has certain properties that are useful, then you can figure out what the behavior of that series is by comparing it to an integral that might be easier to solve. Let's look at some examples. First example, let's figure out if this series converges or diverges. The sum as n goes from 2 to infinity of 1 over n times the natural log of n. Now, first question here, why are we starting this series with n equal to 2? Well, the problem is, first of all, if you tried to plug 0 in, let's just say, then you'd have a 1 over 0, and that would be no good because there's an n at the bottom. Why can't we start at 1? Well, the natural log of 1, that's okay. The natural log of 1 is defined. But the natural log of 1 is 0, and you'll end up with a 0 on the bottom again. So we cannot start with n equal to 1 here. We would have nonsense. But we can start with n equal to 2, and we're fine. Now, this series is not all that different from the harmonic series that we've already studied. If we got rid of that natural log of n, and just had 1 over n for the terms here, this would be the harmonic series, and we already know that series diverges. And the trouble with that series is that the terms are getting smaller and smaller and smaller. They are approaching 0, but they aren't doing that fast enough for the actual series to converge and have a finite sum. If the denominator could get bigger faster, then maybe you'd end up with a series where the terms are shrinking fast enough that you do have a convergent series. For example, we've tried 1 over n squared, and that series, the sum of those values, does converge. Well, the natural log of n is an increasing function, so if you put it in the denominator, you are making the denominator get bigger faster than if you just had 1 over n. So these terms are shrinking faster than the terms in the 1 over n series, the harmonic series. Maybe that means this series will actually converge. Let's find out. We can figure this out by trying the integral of this same function. Let's try the integral test. It doesn't always tell us anything useful, but we can try it. Now, first thing to check here is make sure that our function, f of x, which is going to be 1 over x times the natural log of x, the same function that's in our series, make sure that function is continuous. Now, in fact, it is continuous everywhere from the open interval from 1 to infinity. We need it to be used on a closed or a half closed interval, but in fact, we're going to start at 2 this time and not at 1. So actually, I'm going to cross this out. I'm going to say it is continuous from 2 to infinity, including that endpoint, and we're okay. This function is also positive on that same interval, and it is decreasing. Since the x and the natural log of x are both functions that are increasing in the interval that we're interested in, that means that the denominator is increasing, which means the whole function is decreasing, so it is decreasing. Sometimes there's a little more work to figure out whether your function is decreasing or not, but in this case, we're good to go. So we can use the integral test. So let's try it. let's just take the integral. This time we're going to start at 2 instead of at 1. It is okay to move that lower bound, or that initial value of n, higher than it would normally have been. It is okay to do that. So since our series is starting at 2, we'll also start our integral at 2, and that's okay. We'll go from 2 to infinity of 1 over x natural log of x dx. Now we just need to compute this integral, and we can use any of the tools for solving integrals that we know. When I look at this, I think I can use a u substitution here. Let's try it. Let's let u equal the natural log of x. Now I realize that's going to work because I also see a 1 over x appearing in here, and that is the derivative of the natural log of x. In fact, our du is 1 over x dx. So here is our du, and we just have a u on the bottom. So our integral is now the integral of, let's see, we just have du over u. Now, I could change the bounds. I think I'll keep the bounds the way they are, though. Let's just leave them alone. So let's say x equals 2 to x, well, equals infinity. I could say x goes to infinity, but whatever, it's fine. And this is the easy integral. The solution is we end up with the natural log of the absolute value of u, going from x equals 2 to x equals infinity. And we will just plug in our u again. Let's come right up here. So plug in our u, we end up with the natural log of the absolute value of the natural log of x, going from 2 to infinity. Now, this is an improper integral, so by rights I ought to be taking a limit in order to work out what happens with that upper bound here. But I'm just going to fudge it a little bit. We can get away with this. This is the natural log of infinity. Infinity is not a number, but we know what we mean here is the limit as the argument goes to infinity, minus the natural log of 2. Now, I don't really care what the natural log of 2 is. It's just a number. But the natural log of infinity, well, the limit as your x goes to infinity of the natural log of x is also infinity. This is going to be the natural log of infinity, but that's just infinity. So, the integral diverges. In fact, let's write that down explicitly. Make a little room for myself here, and we can say the integral diverges. So therefore, what does the series do? The series also diverges. And that's our answer. This series, the sum as n goes from 2 to infinity of 1 over n times the natural log of n, diverges. And we're done. Here's another example. Does this series converge or diverge? The sum as n goes from 1 to infinity of 1 over n squared plus 9. Now, again, we can check here. Our function, f of x equals 1 over x squared plus 9, is continuous everywhere. There are no places where the function's even undefined. It certainly is continuous everywhere. So that's good. Is it positive? Yes, x squared is always positive, or 0. And if you add 9 to that, then you get a number that's always greater than 0. So 1 over that's always greater than 0. Now, if you were to graph this function, you'd get something that looks a bit like this. Sort of a vaguely bell curve shape. It's not the same as the actual true bell curve, but it's that kind of shape. You can use all the tools that you know from Calc 1, to graph this function. You could also take the derivative of this function and check that it is decreasing where? It's decreasing everywhere to the right of 0. Decreasing on the open interval from 0 to infinity, which therefore means it is decreasing on the interval from 1 to infinity, including the 1. So it does satisfy the requirements for the integral test. Okay. You do need to check these 3 things before you try using the integral test, because if one of these things is not true, then the conclusions we draw from this are total nonsense. The integral test only works if these things are true about your function. And again, you can always move that lower bound, or that initial value of n, you can always shift that left or right a little bit, and the integral test will still be true in that case. But your function still needs to be continuous, positive, and decreasing on the interval that you're actually integrating over. Otherwise, it's no good. So let's do the integral test. So we'll compare this function to the integral from 1 to infinity. We are starting at 1 this time, of 1 over x squared plus 9 times dx. And we just need to solve this integral. Now, this integral is not too hard to solve. If it were 1 over x squared plus 1, you would recognize that as the derivative of the arctangent function. The fact that we have a 9 instead of a 1 here changes it a little bit. You could use trig substitution here. But you might also already remember or be able to look up in one of your integral tables what the integral of this function is without having to go through the process of trig substitution. If you do that, you'll find that what you get is, well, let's see, 9 is 3 squared. We're going to end up with 1/3 arctangent of x over 3. Going from 1 to infinity. So let's plug in our bounds here. We're going to have 1/3 arctangent of infinity over 3. Again, we are kind of cheating here by just plugging infinity in as if it were a number, but we understand that what we mean here is a limit, and we can get away with kind of fudging the notation a little bit, as long as we are having the right thinking, and as long as we don't do anything that actually is not true or does not follow logically from what we're starting with. Right, minus 1/3 of arctangent of 1/3. Now, arctangent of 1/3, I don't know what that is. What angle has a tangent equal to 1/3? I don't know, but I don't care because I know that it's a number. So this is a number. A finite number. Arctangent of infinity over 3. Well, infinity over 3 is just infinity, right? What is the inverse tangent of infinity? What is the limit as the argument goes to infinity of arctangent? Well, that's going to be, if we draw a little graph of our curve here, the arctangent function here looks a bit like this. This is just plain old y equals arctangent of x. And the limit as x goes to infinity is actually a finite limit right up here at pi over 2. So the arctangent of infinity essentially is pi over 2. We have 1/3 of pi over 2 minus some other number. Now, 1/3 of pi over 2, that's pi over 6. Point is, that's a number. And I don't actually care what the actual resulting number is. I know that my entire integral, this entire infinite integral, this improper integral, gave us a finite value in the end. So the integral converges. And that tells us that our series converges. What is the sum of the series? I don't know. it is not the same as the value of the integral, because we're doing two different things. We're adding up a bunch of terms versus finding the area under a curve. Those are two different things. The integral that you do in the integral test usually gives you a different value than the sum of the series. However, it's usually going to be somewhere close, and you can use the integral test in some cases to approximate the sum of the series. We're not going to go into that right now, but just note that it's possible. Okay, so all I really care about right now is I don't care what the actual sum of the series is, I just care that it has a sum. So we're done. Another example, let's look at the series. The sum as n goes from 1 to infinity of 2 to the n over n factorial. And remember, n factorial is the product of all the numbers from 1 up to n. So 3 factorial will be 1 times 2 times 3, etc. And of course, don't forget that 0 factorial is actually 1 and not 0. So, does this series converge or diverge? Well, here's the problem. What is the function that we're interested in here? Our function would have to be f of x equals 2 to the x, that part's fine, over x factorial. Now, 2 to the x is defined for all values of x. In fact, 2 to the x is continuous everywhere. But x factorial only works for whole numbers. X factorial is only defined for whole numbers. It is not even defined for fractions, irrational numbers, and anything else, so it is certainly not continuous. So this whole function is not continuous. So we cannot use the integral test. So that's a problem. We can't use the integral test, so we actually don't have any tests yet that will allow us to handle this function, or this series. It turns out this series does actually converge. But to prove that, we will need to use the ratio test, and we won't get to that until section 11.6. So we can't use the integral test here because our function is only defined for whole numbers, and therefore we can't even solve the integral. In fact, even if we wanted to take the integral of this function, we couldn't do it. We don't know how to integrate any function that involves factorials because, of course, a factorial is not a function defined on all real numbers, or even an interval of real numbers. So we don't know how to integrate this function, and it doesn't even satisfy the requirements of the integral test. So this is why the integral test is somewhat limited, because it only works in cases where you actually can integrate the function and where the function satisfies these requirements. It has to be continuous, positive, and decreasing on the interval from 1 to infinity or whatever you're going to integrate over. Let's look at one more example. So the series, the sum as n goes from 1 to infinity of cosine of n over n. Now, this one again, can we use the integral test? Well, no, we can't. Well, this function is continuous. F of x equals cosine of x over x. This function's continuous everywhere that it's defined. It is undefined at 0, but if we're not going to look at 0, then we're fine. It is continuous on the interval from 1 to infinity. So that part's okay. What about being positive? Well, no, it's not, right? Cosine of x is sometimes positive and sometimes negative. It depends on what values you plug in. It is not always positive. It is sometimes positive, sometimes negative. And in fact, it's going to fluctuate back and forth forever. So we can't even say that after a certain value of n, it becomes always positive. It doesn't. This is always going to be sometimes positive, sometimes negative. Now, it is true that the limit of the terms is 0 here, because cosine of n is always between -1 and 1, and then you're dividing by n. So the larger n gets, the closer these terms get to 0. But that's not enough to tell us that the series converges. And it's certainly not enough to allow us to use the integral test. So we cannot use the integral test here. Okay. And the test for divergence is not going to tell us anything because the limit of the terms is 0. And as we know, we don't learn anything from the test for divergence if the limit of the terms is 0. So the series might converge or it might diverge. I'm not actually quite sure if this series converges or diverges. I suspect that it will converge, but that it will not converge absolutely. We'll talk about those definitions, what that means, in a later couple of sections next week. So these are just a couple of examples of cases where you can't use the integral test because the requirements for the integral test are not satisfied. So it works well for some series, doesn't work for other series. That's why we have other tests that we can use, and we'll talk about a few more tests very soon.